Okay, now we're going to put all our analysis and rules together to analyze a few very useful circuits using an op-amp. These circuits won't have infinite gain. They'll have finite gain, but they'll be very regular, and we'll use them often, and you should memorize the way they look. So in the first case, we are going to put an input into the negative side. Of course, the feedback always goes to the negative side because it's a negative feedback circuits that we're talking about here in the amplifier. So first we use rule number 1, that V plus equals V minus, and that the non-inverting input is connected directly to ground. Well, if V plus equals V minus, that means this must also be at 0 voltage. Now, we say that that's a virtual ground. Note that it is not a ground in that no current flows directly from A to ground. Normally when we say that things are all connected to ground, we say that they're actually connected. Current could flow from one to the other, but that's not true in this case. It is true that the voltage at A will be the same as the voltage at ground, 0 in other words. Okay, so that's one thing we know. We know the voltage at point A. Presumably we know the voltage at point V in. The second rule, no current flows between plus and minus, means that at A there's really only 2 leads that we need to worry about, this one and that one, so that all the current flowing will flow from like this and up through here like that. So that's the only path for the current. Of course, it could be flowing this way, but then I would be negative. That's the only difference. So the current can only flow between here and here. None can flow this way. So putting those together, we can calculate what the current should be. So the current in R1 is just V in minus VA, which is 0. So V in minus 0 divided by R1. So that's the current flowing this way as the arrow shows it. Now that same current flows through R2, so we can calculate what the what the voltage out has to be. In this case, the current is flowing in this direction, so we take 0 minus V out as our voltage drop, and then that's over R2. But so we get rid of the 0, and we have minus V out over R2. Now setting the two currents equal to each other and then doing a little bit of rearranging, we find that V out is minus R2 over R1 times V in. And again, that's just because we flow down to 0, then we keep going down past 0. That's the negative sign, and the relative sizes of R1 and R2 make this bigger than that, smaller. So we can actually think of this as a voltage divider, right? A is in the middle of V in and V out. It's just that we can fix with the op-amp, we fix A to be at 0 voltage. You can think of this like a first-class lever where you put the fulcrum at the middle. That's our ground node. It fixes that point. If we push down here, we push up there. That's the negative sign here. If this side if R2 is bigger than R1, then we get a big increase. A little push down makes a big push up. So that's the negative op-amp amplifier circuit. We make a positive amplifier. In this case, the input goes into the non-inverting. Remember, in the negative case, the input goes into the negative. In the positive case, the input goes into the positive. The feedback, of course, the feedback loop always goes to the negative. So here's the basic positive op-amp. So we go through our 2 rules again. So rule 1, V plus equals V minus, means that node A connected directly to V minus is the same as V in. And then R1 and R2 still form a voltage divider, normal voltage divider, where we have V0 down here and VA here. So let's write down the voltage divider equation, which says that V in, or VA, is V out times R2 over R1 plus R2. That's our voltage divider equation. And so just rearranging that, because we want V out and not V in, we just move this over to the other side. We see that there's an R2 over R2 here, so that's 1. So V out is just 1 plus R1 over R2. This is first of all, notice that if R2 goes to infinity, which means that this is an open circuit, this is exactly a voltage divider. In that case, R2 goes to infinity, this term goes away, and we're just left with the 1, so Vn equals V out. This is also a lever, because every voltage divider can be thought of as a lever system. Here, we fixed 0 down here, and we're moving here, this part up here, so that V out can move a lot, and it has to move more than the voltage at A in this particular situation. So that's our positive and negative amplifiers. We can do some things. So with the negative amplifier circuit, you'll notice that all the current has to flow through R2 in this situation. So if we have a number of different inputs, all that current has to flow here. This node is still 0, so basically we add all those currents, which means if these are all the same resistors, we divide that out, and we get that we just sum up the voltages in this case, where the resistors on all the three are the same. And then we just have a negative amplifier circuit. We can also do interesting things with capacitors. In this case, it's still negative feedback, but through a capacitor. The first half is just like the negative amplifier. A current will flow from V in to 0 through R1, and we know how much current because of the just Ohm's law. All that current builds up on the capacitor. Where else can it go? And so the voltage there is just the integral of that circuit divided by RC to make the units work out. RC has units of time, as we'll find out later. Here's another value of time, and then the voltages match. So basically, the voltage here is an integral of the current because all that current builds up as charge on the capacitor. If we switch the resistor and capacitor, now the current that flows here depends not on what the voltage is, but how it's changing. In that case, we have dV, there should be a D here, dV in dt will create a current across the capacitor of value C times that change. That current will then flow through R1 and give it the voltage out with the minus sign.